The topic of my presentation is towards efficient use of spectrum. And here's an outline. So I will start by trying to answer to the question, why should we use the spectrum, radio spectrum more efficiently in the future? And then look at it, how is it actually being used currently? And so one way of trying to improve the efficiency is to share the spectrum, so allowing multiple systems to use the same spectrum at the same time. So for that we discuss the most common way of sharing the spectrum. And then as a case study we will look at the use of TV white space, where currently the regulators in US and Europe are setting rules on how to access the spectrum. So how to basically use the TV spectrum also for secondary service. And then we try to draw some conclusions in the end. Okay, so here are some predictions on the growth of traffic. So internet traffic itself is growing something like 32% per year. And then the mobile data itself there are some different predictions, but the predictions are that there is 26-fold time increase in the traffic volumes. So in order to meet this kind of increased traffic demand, then the capacity of the mobile system should be increased quite a lot. Also, there are new type of traffic entering the system, so this so-called Internet of Things. So we have various sensors and other kind of devices ranging from fridge to cars and such, or industrial plants that are accessing or being connected to the internet through wireless communication system. So clearly one of the limiting factors for this is the availability of radio spectrum. There's also one limiting factor which is very important nowadays, is the availability of energy. The ICT systems actually currently are in charge of maybe causing 2% or such. There are different kind of predictions on how much, but they currently produce about 2% of the greenhouse gas emissions, and with this growth predictions of traffic, then that is going to increase as well. But today I will focus on the spectrum availability part, but we are also working, of course, with the energy-related issues. Okay, so here we see a spectrogram. So this axis here is time, and here is frequency, and these colors indicate received power. So this is a measurement that has been done by Ficora. So this is from one master thesis that was made for me. So these blue areas, there we see very little activity, and then when we have some other colors, then there is a lot of activity. So this part here is a cellular radio system where we see that there's a lot of traffic, and these bands here are the terrestrial TV bands. So it seems that there is quite a lot of blue things, and this blue areas is something which we call white space. So a naive approach to this kind of improving the spectrum efficiency is just, okay, there's free space here, so let's start using it. And there are different kind of approaches for using that, but the most common is something which is called interwave access. So we see in time or space these kind of holes where there are no other systems, then a secondary access could be possible. So here we see, for instance, in time domains, this is the power of the primary system, so there's no primary system present here, here, or here, so we could basically have a system which is using different parts of the spectrum as the time progresses, or it could be space. But in practice, actually, it turns out that these free spaces here, they are usually related to some protection margins and protection bands, or they could be related to some other systems which have very high requirements on the interference that they can tolerate. So, for instance, the radar systems or such. So it's not so straightforward that I just measure the spectrum and see that if there's sort of white space, then we just access. But there are more challenges, since once we access, we should try to protect the primary system there as well. So we can have certain definitions to look at that, and when do we actually have such a wide space that we can use? And this is what we call spectrum availability. So basically the spectrum is available if we can transmit on that particular band without causing excessive interference to the primary user of that band. And that is also very much related to the regulatory rules. So in principle, all the systems have been built in such a manner that they have some interference margin because they are interfering themselves as well. So then it's the question of like how much margin they have. So to find if there's enough margin for the secondary system, then we could add there more interference, basically. That is the sort of simplest approach. There are different approaches as well. So then, assuming that the spectrum is available, then we also have the problem of detecting that it's available. So this is the concept of spectrum opportunities related to that. So we should also be able to detect the availability of the spectrum and detect that hopefully in a reliable manner. So currently there are two approaches for detecting the availability of the spectrum. Especially in the academic, there has been a lot of interest in this sensing-based approach, where we basically try to measure the spectrum and detect the signals and classify and estimate the signal levels. The industry is more looking at currently, and the regulation is more going towards the database-based approach, where we have a geolocation database which contains the information of the location of all the transmitters and has models on the radio propagation and the criteria on the primary system characteristics so that we can compute what kind of powers, for instance, could be possible for the secondary systems to use. So if we first look at the sensing approach, the benefits of this kind of system is that it doesn't require any infrastructure. So the system could be an ad hoc system which self-organizes, which has benefits in certain applications. But there are some major problems, and that is the sort of hidden terminal problem. So here we have a TV tower, and this is the TV receiver. And then there's some obstacle which is shadowing the radio path. And now if you are in this position here trying to decide whether this spectrum is available for us just by sensing, then the signal from the primary system is very much attenuated due to the shadowing effect. Whereas there could be even line of sight path to the victim receiver. So if we then fix, for instance, the probability of misdetecting the signal, so that should not exceed some protection criteria. And then look at the decision criteria for a single sensor here to make a decision whether the primary system is there or not. Then here we have seen one numerical example where there's a number of collected samples, and this is the probability of false alarm. So basically, if you have just single sensor trying to make the decision, then we have the probability of false alarm being almost 100%. So this problem can be, of course, solved by allowing multiple secondary systems or sensors to collaborate. So if there would be a large number of sensors here, which would be far enough apart from each other to see independent shadow fading, then we could quite reliably still detect the system. So then the other approach is to use databases. And in database case, we have now centralized control over everything. So that is the good feature, but then again, you need to have this infrastructure to handle the control of the system. So, and there, of course, are some practical problems also related to their database systems, like how often the systems should report on their activity. So how often, for instance, we update the activity of the primary systems. How often should the secondary system make an inquiries and such. But this seems to be now the approach that is currently taken by the industry. So there are now quite many companies have been founded for handling this kind of geolocation spectrum databases. And this is, there are quite big players such as Google also interested in this building such a databases. There are currently some issues open. So, for instance, on how to control the aggregate interference, especially in the sensing case, but also in the database approach as well. So, the ECC and FCC are currently setting up rules on how to access the spectrum. The focus is on TV white space, so trying to reuse the terrestrial TV bands. Somehow, the general approach that is used for TV white space could be generalized to other bands as well. But currently, this is the band of interest where the first cognitive radio systems will appear. So FCC in US has been the first to suggest the secondary usage of TV spectrum. Their FCC rule is rather simple. So if this is the coverage area of the TV broadcast cell, then there's certain protection area around that, and then the spectrum could be used outside that area. So there's different ranges whether you're looking at the transmission on a co-channel or the adjacent channel. FCC rule also has specified this criteria for sensing-based approach, but due to this fact of shadowing, then they have been very conservative. So there has been very little practical attempts on building such systems that are based on sensing. So the FCC rules are rather simple, but they don't control the aggregate interference at all. So they only look at that if you are outside this region, you can transmit with fixed power, and there is no control on how many transmitters are transmitting outside. Then the European Union is also trying to specify rules for accessing the radio spectrum. The ECC rules are more complicated. So basically take the coverage area of a TV transmitter and then set a limit on the area location probability, meaning that the probability that we can receive the TV signal here. So there's a certain constraint that this probability must be high enough. And then we basically take a grid of points, so which are called pixels, which are something like 250 meters times 250 meters squares, and say that, okay, in this particular square, if you are going to transmit, then you can use certain transmission power. So here's a solution of the equations that describe what kind of power can be used. And the impact of aggregate interference is just taken into account by adding some interference margin there. So there's one free parameter that needs to be decided. Then on co-channel, so if you are located inside the coverage area of some TV transmitter, but on the co-channel, then they define a reference geometry that basically make an assumption that you are close at certain distance from the victim receiver. So then the power levels become quite conservative once again. So we have made some studies on what would these kind of regulatory rules actually mean if we deploy them in Finland. So here we see the number of available channels with the FCC and ECC rules. So FCC rules has these protection regions around the TV cells, which means that the number of channels are going to be less than in ECC case. So in ECC case, quite many channels are available, but the power levels are more restricted. Then we made a comparison, what does it mean in terms of capacity for the secondary system. So also, it seems, although here we have more channels and restricted power, so we get slightly higher capacity. This figure here shows the TV signal signal quality, and this is the probability that the quality is below this threshold. So there's certain requirement that the TV signal should exceed 17 dBs in order to be so that we can decode it correctly. So then, as we mentioned, there are the regulatory rules define certain margins that need to be set. So it is actually quite sensitive, though these different lines here correspond to different values of those margins. So if we pick too small a margin, then there's quite high probability that the quality of the TV receivers become too low. So if you pick a very high margin, then there is very little power available for the secondary systems. So this seems a bit challenging tuning problem in terms of these parameters. So we currently are working on how to solve this and made also some proposals on CEPT on this matter. So basically what we have been doing is we take the TV cell, the coverage points here, and it turns out that we actually can compute, given this probability of protection criteria, so that the TV signal should be greater than or equal. So there seems to be some font problem here. So we have set the criteria on the probability of the TV signal being good enough. So from that, it turns out that we can find a bound for the received interference. So as long as the mean received interference is below this bound, then we can show that actually this probability holds in case of log normal shadow fading. Then another issue is that we would need to control the power for multiple transmitters, but these areas can be rather large. And if we deploy very dense systems like cell radius of, say, 100 meters, then we would have thousands or tens of thousands of transmitters in some area. So if you need to compute separately the power from each of them, that can be, it's of course doable, but can be computationally quite challenging. So we are currently working on ways of trying to describe the areas in terms of power density instead of looking at the individual transmitters, but rather sort of a distribution of transmitters. So now we can formulate some sort of resource allocation problems where we treat the interference margin here at the coverage area as a resource, which is then divided among the secondary systems. So here's an example of 3 sort of areas deployed in the area of Jyväskylä. So we can then maximize, for instance, what is the power available in each of these areas, such that the primary system protection criteria is met. Or in rather slightly larger extent, then here's one particular example of take one TV channel and deploy a secondary system. So there's a different site density or cell range. So in the areas, this basically reflects the population density in Finland. So in urban areas, we use smaller cells, and then in very rural areas, larger cells. And then utilize the same methodology to find what is the power available for the secondary systems, so that the primary systems, which are here, these are co-channel, and here are adjacent channel primary transmitters. So we need to protect them. So, okay, if we just optimize the power allocation from the primary system perspective, then in those areas where we are using larger cells, we could use slightly higher power. Then if we actually add there a constraint on the interference between the secondary systems themselves, so the self-interference, then it turns out that the solution is more or less unified power density over the whole country. So then it turns out in terms of capacity, this is the capacity available on the cell edge. That, okay, there seems to be on this particular channel quite a lot of capacity available, especially in the northern part of Finland. And this is then when we look at what it means when we take the population density into account. So then the capacity divided by the population, then it seems that okay, this would be rather feasible way of making a mobile sort of rural broadband access. But then on the city areas, there is less capacity per user. So in order to increase this capacity here in the dense population area, we need to look at more smaller cells. So perhaps it would be feasible maybe to deploy kind of a local area networks on this band. Okay, so to conclude, we could basically utilize the spectrum more efficiently by allowing secondary access, but one of the major challenges is to protect the primary system against the interference of the secondary systems. And the current regulatory rules have the problem that they are just looking one transmitter at a time. So we really need mechanisms for that take the aggregate interference of multiple secondaries into account. And this is one area where we have made some proposals that basically to consider how much interference the secondary can tolerate and then use that as a resource for the secondary system. And what the focus on my talk today was on digital television, but there are many other candidates bands, such as the radar bands, where similar approach could be used. And as a sort of byproduct of this, our analysis, we have been using Finland as a case study. So it seems that in TV bands in Finland, it would be feasible to deploy some sort of rural broadband, and then in dense populated areas, some sort of local, wireless local area system type of networks. Okay, thank you for your attention.